The headline promises a tour of the first U.S. underwater habitat, triggering images of sci-fi living quarters where humans sleep on the seafloor. But the engineering reality at 200 meters deep tells a different story. Here, human repair is impossible, and radio communication fails completely. This isn't just a room for people, it functions as an autonomous machine that must keep itself alive without external help. The real narrative shifts from a habitat tour to an analysis of how robotics solves the triad of extreme pressure, power scarcity, and maintenance logistics where no diver can go today. To understand why this is possible now requires examining the environment we are trying to conquer. At depths exceeding 200 meters, the ocean floor presents a hostile landscape where physical infrastructure must survive without human hands nearby. The traditional approach relied on tethered vehicles that drag umbilical cords across the seabed, creating drag hazards and limiting range in tight spaces around habitat structures. These limitations mean that if a seal fails or a sensor malfunctions, a crew cannot simply swim out to fix it because the pressure differential is too great for safe human intervention without specialized equipment that takes days to deploy. The solution lies not in building stronger walls alone, but in creating an immune system of machines capable of operating where humans physically cannot reach. The first pillar of this new engineering reality is autonomous maintenance and robotics integration designed specifically for high-pressure environments. We are moving away from the idea that a habitat needs constant human labor to function. Instead, systems like the proposed Sentinel habitat rely on robotic intervention performed by specialized manipulators trained through physics-based simulation before they ever touch real equipment. Researchers have developed simulators using advanced frameworks to train operators in virtual reality for seabed interventions involving critical tasks such as swapping sensors or repairing seals with extreme precision. This training ensures that when a robot is deployed, it executes maintenance without risking human life or damaging the fragile infrastructure of the habitat itself. The goal is to perform these delicate operations remotely, ensuring that the habitat remains operational even when no humans are present inside its pressurized hull. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This shift in capability addresses the critical challenge of operating without tethers. Traditional underwater vehicles require physical cables for power and data, which creates a significant bottleneck for maintenance tasks inside or around complex habitats where cords can snag on valves or get caught in debris. Next-generation systems like Aquanaut demonstrate the necessity of autonomy by transforming from a streamlined submersible into a humanoid form to manipulate infrastructure without these constraints. This dual-mode capability is essential because if a habitat's external power supply fails, an autonomous transformer robot can physically engage with internal systems in ways tethered vehicles simply cannot achieve. The ability to change shape allows these machines to navigate the confined spaces of a pressure vessel or reach around complex piping networks that would be inaccessible to a rigid vehicle, effectively acting as the hands and feet of the habitat when human presence is impossible. Once inside this environment, sensing becomes just as critical as movement because satellite signals do not penetrate deep water. Without GPS, robots must rely on biomimetic sensory arrays inspired by fish lateral lines to detect subtle changes in water pressure and flow patterns. This technology allows for coordinated group navigation and precise positioning even in zero visibility conditions where cameras are useless. The success of this approach is evidenced by missions involving autonomous vehicles retrieving seismic data loggers at depths exceeding 2,500 meters, despite hazy water and strict battery constraints. These systems can feel their way through the dark ocean, detecting currents that might otherwise push them off course or cause collisions with sensitive habitat components. This sensory capability transforms a blind robot into an intelligent operator capable of performing complex tasks in total darkness where human operators would be completely disoriented. The convergence of these technologies explains why we are not yet living underwater despite decades of speculation about sci-fi cities beneath the waves. The bottleneck is no longer just pressure resistance or basic life support. It is the ability to program and deploy resilient machines that can fix problems before they become catastrophic failures. We have moved past the era where a habitat was merely a pressurized room waiting for human repair crews to arrive from the surface. Instead, we are building an ecosystem of intelligent systems that act as the immune system for physical infrastructure in hostile environments. The engineering challenge now is creating machines that are as resilient and autonomous as the humans who would eventually need them to survive long-term operations at depth. This evolution redefines how we view deep-sea exploration, not as a quest for new living spaces, but as an exercise in extending our mechanical reach into zones where biology fails. It requires a fundamental shift in mindset from building static structures to deploying dynamic networks of autonomous agents that can adapt and repair themselves over time. The future of underwater infrastructure depends on this transition, paving the way for expanded mining operations, permanent research stations, and perhaps eventually human expansion into deeper waters. Until these mechanical intelligence systems are fully matured, our presence in the deep ocean will remain limited to short-duration missions supported by surface vessels rather than self-sustaining autonomous habitats. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.